Hey guys, Miss Marusik here, and in this video we're going to talk about the strength of acids and bases. Now, I would hope by now you have memorized your list of strong acids and strong bases. And if you haven't, then you better go memorize that list as soon as possible. However, let's say I have an acid or base that's not on that strong list. At that point, I assume it to be weak. But even if an acid or base is considered weak, some are stronger than others. There's different levels of being a weak acid or base. And those levels are tied to how much of that substance will change into ions when I put it into a water solution. So with that said, for an acid, the greater the amount of acid that dissociates, or the more proper term, ionizes, the greater the value of Ka will be. Now remember, a greater value for an equilibrium constant like Ka would indicate more product, here meaning more ions when it is in a water solution. So that would indicate a stronger acid. We can make the same statement about a base. The greater the value of Kb for a base, then that would indicate a stronger base. Now, there are correlations between the strength of an acid and its conjugate pair, or a base and its conjugate pair. So to kind of put that into perspective, let's look at the chart below. So what it wants us to do on this chart is to indicate the direction of strength increase of the acids with their conjugate bases. So we notice here a huge list of acids all given with our Ka values. And if we remember the statement up above, the greater the value of Ka, that would indicate a stronger acid. So our largest values for Ka are here at the top, while our smallest values are here at the bottom. So that means that we have an increasing acid strength as I move up this chart, which should make sense because we notice at the top of this chart, we have hydrochloric and nitric, and hopefully we recognize those as being two of the acids that are on our strong list. However, look what happens with these conjugate pairs. Notice that on the conjugate pair list, here my KBs are really small at the top, and they get bigger as I work my way down, meaning that I have increasing base strength moving down this chart. So think about what that means. If I have a really strong acid, then it has a very weak conjugate base. If my acid is not quite as strong, then I have a little bit stronger conjugate base. Now, this actually helps us out with regards to calculations. Think about the way we did calculations for pH for hydrochloric and nitric. We essentially said that all of our substance is going to go and make ions. And so we just used stoichiometry to figure out what that ion concentration would be in order to get the pH. We didn't even take into consideration that the conjugate base that we form might go back and form acid. Why? Because it does so such a small, insignificant amount that it doesn't matter in terms of the calculation. However, when my Ka values get smaller, now my Kb values get more significant, meaning that while the forward direction might be the dominant direction, I might still have some conjugate base going back and making acid. And so both directions need to be taken into consideration when I'm trying to calculate the pH. And so that's why when we're calculating pH on a weak acid or base situation, we've got to use equilibrium to do so. All right, let's keep on looking here at some of the other statements. First off, it does say to notice that for the strong acids, the Ka values were greater than 1, which indicates that equilibrium heavily favors the products, in this case, the ions that I'm making in the solution, which is why we say that those acids essentially ionize 100%. So again, when those Ka values are so large like that, we assume that we're really not doing any kind of equilibrium whatsoever, that essentially we're just going straight to product. Something else we noticed on our table is that the stronger an acid is, the weaker its conjugate base would be. However, the same statement could be made for a base. The stronger a base is, the weaker its conjugate acid is. Now, the strength of a base is determined by how strongly the H plus is attracted to be gained by the structure. So the more strongly your hydrogen is attracted, then that means you have a stronger base, and so the greater Kb value you would have. By the way, this would also result in a more stable conjugate acid, which is part of what's driving that gain of the H plus in the first place. You're creating something that's very stable in the end. However, the strength of an acid is a little more complicated. It is tied to how easily the hydrogen is removed, but there's a lot of reasons why hydrogen might be more easily removed from a structure than others. And so that's what we're going to talk about here in a little bit. However, the more easily that hydrogen is removed, the stronger the acid would be, the greater the Ka value would be, and that would result in a more stable conjugate base, which again is what's driving that reaction in the first place. However, as I mentioned, there's various reasons why hydrogen would be more easily removed from some acids than others. So with that said, let's go ahead and flip the page. All right, so we're going to start off by talking about binary acids. And those are acids that contain two elements, the hydrogen along with another element that would be our negative anion. They do not contain any polyatomic ions. For binary acids, there's two factors that play a role in acid strength, either the bond length, which is tied to bond energy, or the bond polarity, which is tied to differences in electronegativity. And which of those you use to justify why one acid is stronger than another determines on what elements you are comparing. For example, if I'm trying to use bond length to compare, then I need to use that when I have elements that are in the same group or column on the periodic table. For example, here I have fluorine, chlorine, bromine, and iodine. I notice that those are all in group 17. They're all halogens. And so I want to use bond length to justify why some of these are stronger than others. So they start us off here by asking, using the values of Ka, which of the acids is the strongest of those listed? Well, I know that most of you should know that hydrochloric, hydrobromic, and hydroiodic are all considered strong acids. But if you look which one is the strongest, that would be the hydroiodic, because it has the largest Ka value. So therefore it would be the most ionized, even though hydrochloric and hydrobromic are essentially almost as ionized. And it asks next, does the strongest acid have the largest or smallest bond length? And if I look at the bond length values here in picometers, I notice that hydroiodic does have the largest bond length. And it asks what causes this bond length difference. So remember, when I have elements that are in the same group on the periodic table, what causes the difference in bond length has to do with the number of occupied energy levels. Hydroiodic has the most occupied energy levels in that iodide in comparison to the bromide, chloride, and fluoride in the other acids. And so therefore it would have the largest bond length. It next asks, would you expect a longer bond length to have a higher or lower bond energy? So let's think back for a minute. If I have a longer bond length, that distance between the two nuclei, the internuclear distance, is greater. And hopefully we remember Coulomb's law. If that distance is greater, then our force of attraction should be decreased. It should be a weaker attractive force. And if I have weaker forces, then I should have a lower bond energy. So here's what basically happens. When I have binary acids with anions in the same group, the stronger acid will be the acid with the longer bond length and the lower bond energy. The reason why is because the weaker bond between the hydrogen and the element will allow the hydrogen to be more easily removed by water, and that will result in a stronger acid. Remember, I want more of that H to be capable of being removed off in order to be stronger. And so if that bond is weaker, that hydrogen can be plucked off by water more easily and create more ions in my solution. All right, let's say though I have some anions that are in the same period, the same row on the periodic table. When I have the same period, the problem is that I don't get these big differences in bond lengths anymore because there's no change in the number of occupied energy levels. So there's got to be something else that's causing the difference here, and that has to do with bond polarity. So again, I notice a list of Ka values here, but this time, if I look at what's with the hydrogen, I notice each time I'm seeing elements that are in the same period. So they gave me instead here differences in electronegativity. So it says here first, using the values of Ka, which of the acids is the strongest of those listed? And that would be the hydrofluoric because it had the largest Ka out of these acids. So next, it asks, does the strongest acid have the largest or smallest difference in electronegativity? Well, if I look here, it has the largest difference in electronegativity between the hydrogen and the fluoride, which should make sense because we know fluorine has the highest electronegativity out of any element. So it makes sense that that difference there would be quite large. So here's what happens. When I have a larger difference in electronegativity, that indicates a more polar bond. And if I have a more polar bond, then I'm going to get a lot more attraction occurring to other molecules, including, most importantly, water. So here's what happens. For binary acids with anions in the same period, the stronger acid will be the acid with the more polar bond, as indicated by the greater difference in electronegativity, which will cause stronger attractions to water. And if I get those stronger attractions to water, the hydrogen will be more easily removed by the water, and that will result in a stronger acid. Now, I want to point out what we've kind of talked about here and reason out why hydrofluoric is not on the strong list. Because I always get the question, well, Miss Marusik, hydrochloric, hydrobromic, hydroiodic, those are all strong. So why is hydrofluoric not? Even though it has a really big difference in electronegativity, meaning it has a lot of attraction to water molecules. Unfortunately, it also has a very short bond length. And so that increases the strength of that bond and makes it very difficult for water to peel off that hydrogen, even though there's a lot of attraction between them. So we have to be really careful here because this really shows the difference between bond strength and bond polarity. I can have a bond that's really strong and really difficult to peel apart, but it can have strong or weak attractions then to other molecules. I have to be very careful that there is a difference between how much energy it takes to break that bond versus how much pull is within that bond, because they're different. Hydrofluoric has a lot of pull, but that bond is also really strong, and so that is why it is not considered to be a strong acid. All right, with that said, let's go ahead and flip the page and talk about oxyacids. Now, an oxyacid is an acid that has a polyatomic ion that contains oxygen in it. So we still have the hydrogen at the front, but now we have that polyatomic ion instead of just a singular element. And for oxyacids, there are two factors that play a role in the acid strength, either the number of oxygens or the electronegativity of the central halogen. So again, we'll have a special situation for each of those of when we consider which factor. However, both of the factors result in differences in electron density. The electron density is basically how tightly packed are your electrons in one region of your molecule versus another. If we have a really packed, tight electron density on one side of the molecule that's opposite of where the hydrogen is going to be lost at. That can lead to a weaker OH bond in the acid and allow that acid to give up that hydrogen a little more easily and be stronger. Now, something to point out that is confusing to people. It says, notice that on oxyacids, the hydrogen is actually bonded to an oxygen in the structure, not to the central atom. So if you look at all these chlorine polyatomic ion acids here, you will notice that the hydrogen is always attached to an oxygen and not to the central chlorine on that polyatomic ion. So be really careful with that. That's a common misconception that people have. They assume that the hydrogen is attached to the central atom when in fact it's not. So let's look at the two situations here. So first off, if the number of oxygens are different, then I want to use that to compare our strengths. So this is used when we have the same central halogen. In this case, all of these have chlorine in it. So we have hypochlorous, chlorous, chloric, and perchloric. And we notice that each time we're going up here, I'm adding more and more oxygens to one side of my particular acid. And you notice those oxygens are getting added on the opposite side away from our hydrogen. So what happens is that because I'm adding more and more oxygens over here, that is increasing the electron density on this particular other side of my molecule. And you've noticed I've tried to indicate that here with some arrows. And you notice as I keep on going across here, I'm showing increasing arrows as I work my way to perchloric. This would have a very great electron density on this side of the molecule in comparison to the hydrogen side. Now, what does that mean for acid strength? The more oxygens I get, the greater the electron density is. And if I have a greater electron density on one side of the molecule, that ends up creating a much weaker bond right here that's easier to break. So now if a water was to come along to this molecule, it would have a much easier time of removing that hydrogen off of something like perchloric or chloric than it would on these other two, because of that very high electron density. So, to summarize here, as the number of oxygens in the polyatomic ion group increases, the electron density is pulled away from the OH bond. You could say the OH bond or the HO bond. It doesn't matter. It's that bond where that hydrogen is that I'm trying to lose. So if that bond now gets weakened, that allows the hydrogen to be more easily removed by water. And so therefore the strength of the acid increases as the number of oxygens increases. So that is why chloric and perchloric are both considered strong acids, but my chlorous and hypochlorous are not. All right, let's now think about the central halogen being different. So you notice on all three of these, I have the same number of oxygens now, but now I have a different central halogen. Here I have iodine, here I have bromine, here I have chlorine. And so when I change that halogen, I end up changing the electronegativity. Chlorine is more electronegative than bromine, which is more electronegative than iodine. So that creates a greater electron density over here on chlorine than it does on these other two acids. And so if I have a greater electron density, that means again, I weaken that hydrogen to oxygen bond with that hydrogen I'm trying to lose. And so therefore it is more easily lost. So again, to summarize here, as the electronegativity of the halogen increases, the electron density is pulled away from the oxygen to hydrogen bond, which weakens the oxygen to hydrogen bond and allows the hydrogen to be more easily removed by water. Therefore, the strength of the acid increases as the electronegativity of the central halogen increases. So this is the reason why chloric and perchloric are strong, but then like bromic and perbromic are not, or iodic and periodic are not, because that chlorine is so much more electronegative that it pulls at those electrons more, creating that higher electron density, which means we end up getting a stronger acid out of the deal. All right, we've got one more situation I want to talk about. So let's go ahead and flip the page. And that situation is polyprotic acids. Now, as a reminder, polyprotic means I have more than one hydrogen that could be removed. And so because I'm removing more than one hydrogen, I end up with multiple Ka values, one for each hydrogen that is being lost. So as an example here, we see phosphoric acid, which is actually a triprotic acid because it has 3 hydrogens that could be removed. So I start off here with H3PO4, and when I remove the first hydrogen to give me H2PO4 negative 1, that has a Ka value of 7.52 times 10 to the negative third. When I take H2PO4 negative 1 and remove another hydrogen, that bumps us down to HPO4 negative 2, which has a smaller Ka value. And then when I take that HPO4 negative 2 and peel off the last hydrogen, that leaves me with my phosphate polyion, PO4 negative 3. And you can see that has the smallest Ka value out of the 3 processes. So what that means is that for each successive hydrogen loss, the value of Ka is decreasing, meaning each of the successive acids are weaker in strength. Phosphoric acid is already a weak acid, but H2PO4 negative 1 is even weaker, and HPO4 negative 2 is even weaker in strength. And the reason behind that is because once a hydrogen has been lost, that charge you're creating now is helping to create some extra attractions within that structure. And so if it's attracting everything a little bit more, it's going to be even harder to remove that next hydrogen. That next hydrogen is more strongly held to the ion and less likely to dissociate. So what that means is that while this first equation, this first ionization is happening some, not a lot, this second ionization is even happening less. And this third ionization is barely happening at all. Now, technically, in a water solution, if I put phosphoric acid in, all 3 of these processes would be occurring, which means that I technically have all of these substances in my solution, but they would not be in equal concentrations because all of these processes are happening at different percentage. So on this example here, it says for phosphoric acid, rank the concentrations present of each of the forms of H3PO4 and its conjugates in the water solution. So I actually put the highest concentration over here, H3PO4. First off, it's a weak acid. Very little of it is going to make product anyway. So the bulk of your solution is going to be that H3PO4. But I'm going to end up making a little bit of H2PO4 negative 1. However, only a little bit of that is going to lose a hydrogen and end up forming HPO4 negative 2. And even a smaller fraction of that is going to end up losing a hydrogen and making PO4 negative 3. So will I have a little bit of this ion in my solution? Sure. But am I going to have very much? No. Most of your solution is still going to be H3PO4, and there's going to be decreasing concentrations as I work my way back through those substances. Now, if our factor in the Ka values between the first, second, and even the third dissociation have a difference of 3 or greater, what that means is that the pH of the acid really only depends on the first dissociation. What I mean by that, if I come back up here, I notice that the difference between this first Ka and the second Ka is negative 3 to -8. That's bigger than a factor of 3. So what that means is that if I was trying to calculate the pH of this solution, I would probably only use this first Ka value to approximate the amount of hydronium that I'm making. Would these other two processes make a little bit of hydronium? Sure, but it's so little in comparison to how much I'm getting out of this first dissociation that those amounts don't really even matter. So that is a trick that you can use sometimes on these polyprotic acids that save you a whole bunch of calculations, is that you can assume that because this value is so great, that most of your dissociation is happening in this first step. And so therefore your pH is mainly based off of that first step. You'll still have to do equilibrium because it's a weak acid, but you won't have to do multiple equilibriums for the multiple steps. Now, one other thing that happens with polyprotic acids is that when you have a titration curve, you actually end up with 3 separate equivalence points. You notice on here we have an equivalence point that is occurring here, here, and eventually here. Those represent the 3 places where hydrogen is being removed. However, that also means you end up with 3 separate half equivalences. Here, here, and here. And if you look at those pKa values, those are tied to your exponents back up here on these Kas. So having an exponent of -3 would mean that your pKa is 2 point something, right? Well, look at where that pKa is, 2 point something. And you'll see that the other ones work out with that same situation. So what's interesting is that if you do a titration process with a polyprotic acid, you actually have to use several different indicators because you'll need a color change to happen at the first, the second, and the third equivalence points. So you'll have to pick different indicators to put in that would change colors at those various pH levels. All right, I hope we're feeling good about notating the strength differences between various acids and bases. If you have any questions or need any help, please feel free to email me. Bye, guys.